Welcome to our Bioprocess Engineering online tutorial on bioprocesses simulation models. Through the Bioprocess Engineering online tutorial series, you gain expertise in the principles of bioprocess engineering and their applications to enzymatic bioconversions, microbial fermentations, and cell cultures bioprocesses. For more details, please visit us at bioprocessengineeringonline.com. In this introductory tutorial on simulation models for bioprocesses, we'll address three questions: why to use simulation models for the design and scale-up of bioprocesses, what types of simulation models are developed in bioprocess engineering, how to construct simulation models of bioreactors. Bioprocess engineers increasingly depend on simulation models for the design, scale-up, and optimization of bioprocesses. In the realm of bioprocess engineering, these simulation models are elaborated with the explicit goal of minimizing the need for extensive experimental work during the research and development phase. This strategic approach not only accelerates the process scale-up, but also serves as a cost-effective means to reduce expenses associated with process development. At the core of the bioprocess engineering simulation strategy lies the creation of simulation models, specifically tailored for reactors that implement the biotransformation step. Specifically, in the case of enzymatic bioconversion, the bioreactor simulator is designed to forecast the temporal changes in substrate, product, and active enzyme concentrations throughout the bioconversion process. Furthermore, these models are crafted to anticipate the impact on bioconversion kinetics resulting from various factors, such as the bioreactor technology employing either soluble or immobilized enzymes, the operational mode of the reactor, batch or continuous, and the two main operational variables, temperature and added enzyme concentration. In instances of bioreactors involving microbial fermentation or animal cell culture, the simulation model is intricately crafted to predict the dynamic variations in nutrients, cell, and metabolite concentrations throughout the cellular transformation process. Furthermore, these models are tailored to foresee the impact on fermentation kinetics stemming from various factors. This encompasses the operational mode of the reactor, whether it operates in batch, continuous, fed batch, or perfusion mode, as well as critical operational variables, such as nutrients, concentrations, medium flow rate, and aeration rate. The simulation models for enzymatic and cellular transformations can be conceptualized as digital twins of bioreactors, acting as virtual counterparts or replicas of the real reactors. Elaborated from experimental data obtained at the laboratory scale, these digital twins play a pivotal role in facilitating the scale-up of bioreactors. By conducting virtual simulations of the industrial-scale reactor, engineers can thoroughly explore and assess its performance under diverse conditions. This process enables the identification of optimal operational parameters crucial for effective bioreactor scale-up. Two types of models are commonly employed in process engineering. The simplest among them are the so-called black box models. These models establish relationships between the inputs and outputs of a system without delving into the internal workings of the system. Black box models find their application in data analysis and experimental design. They prove particularly effective for the statistical analysis of large data sets derived from experiments or industrial processes. However, they possess limited predictive power when it comes to tasks such as designing, scaling up, and optimizing processes. The second category of models pertains to the so-called white box or knowledge models. Unlike black box models, these are built on deterministic equations that encapsulate the physico-chemical knowledge of the system or process. While the development of knowledge models may require a more significant investment of time, They offer crucial advantages in terms of predictive capabilities for bioprocess simulations and scale-up. The initial phase in constructing knowledge-type models for bioreactors involves comprehending the factors influencing the temporal variations of substrate and product concentrations in the examined biotransformation. Typically, the temporal changes in concentrations are subject to both thermodynamic and kinetic constraints or limitations. Thermodynamic limitations play a role in determining the ultimate concentrations achievable. On the other hand, kinetic limitations govern the rate at which concentrations vary, providing insights into the dynamic aspects of the biotransformation process. For biotransformations, as well as for other unit operations of bioprocess, there exist four fundamental phenomena that exert an influence on the temporal variations of concentrations. These four key phenomena encompass biochemical reactions, material transfer, heat transfer, and fluid flow. Together, these four elements play a key role in shaping the rates of material transformation through biochemical reactions, mass and heat transfer rates, and the rates of fluid flow within bioreactors. Let's delve into a more detailed examination of the influencing phenomena that must be considered in the context of an enzymatic bioconversion reactor. In the case of a bioconversion carried out with soluble enzymes, the progression of the bioconversion is exclusively governed by the enzymatic bioconversion reaction and the enzyme denaturation process. On the other hand, when employing enzymes immobilized within particles, the kinetics of bioconversion are mainly influenced by the rate of the enzymatic reaction and denaturation occurring inside these particles. However, this process may also be constrained by the transfer of reaction substrate molecules from the solution into the interior of the particles. Moreover, the rate of solute transfer in the solution is impacted by the flow velocities of the medium around the particles. For a microbial transformation, the temporal evolution of substrate and product concentrations is primarily governed by microbial growth and metabolic activities. In aerobic fermentation, an additional factor, often acting as a rate-limiting step, is the supply of oxygen to the cells. This is contingent upon the solubility of oxygen in the medium and the transfer of oxygen between the air and the medium. Another potential limitation arises from the removal of heat generated by microbial activity during fermentation. The efficiency of heat removal is constrained by the rate of heat transfer at the fermenter's surface. Additionally, the processes of oxygen and heat transfer are intricately influenced by the flow patterns within the medium inside the fermenter. Following the initial step of postulating the influencing phenomena within the bioreactor, the subsequent phase in constructing the simulation model involves deriving the mathematical relations that depict the temporal changes in the concentrations of the various components. This modeling methodology adheres to the concept of the modeling triangle. It combines the material balances for the medium components, reflecting the principle of mass conservation, with the thermodynamic and kinetic laws that represent the underlying influencing phenomena. The methodology for model construction is illustrated through a continuous fermentation process designed for bacterial production using sugar as the primary substrate. The process begins with an initial batch fermentation, where a medium containing an initial sugar concentration, S0, is inoculated with a bacterial concentration, X0. After this initial phase, the fermenter transitions to continuous operation, during which a steady flow rate, Q, introduces fresh medium with a sugar concentration, S feed. Simultaneously, the same flow rate is used to withdraw medium from the fermenter, ensuring that the fermenter maintains a constant volume. The goal of the simulation model is to predict the dynamic changes in sugar concentration and cellular biomass concentration over time during the continuous fermentation process. The temporal variations in sugar and biomass concentrations during continuous fermentation are determined by microbial transformation kinetics. Consequently, accurate modeling requires a thorough understanding of the kinetic laws governing bacterial growth and sugar consumption. The specific growth rate of bacteria depends on the sugar concentration in the medium. A commonly used rate law states that the growth rate reaches a maximal specific value at high sugar concentrations, but decreases under low, limiting sugar conditions. Similarly, the specific rate of sugar consumption is generally proportional to the cell-specific growth rate, reflecting the direct relationship between substrate utilization and biomass production. In addition to the microbial kinetic laws, the bioreactor modeling relies on the instantaneous mass balances for the sugar and cellular biomass. Material balances express the fundamental principle of mass conservation. For a component, the instantaneous mass balance involves four terms: the inlet rate from the outside to the inside of the reactor, the outlet rate from the inside to the outside of the reactor, the biotransformation rate, that can be the production rate for a product or the consumption rate for a nutrient, and the internal variation rate, that expresses the rate of the component's internal mass variation. The instantaneous mass balance relation is written as inlet rate plus or minus production rate equals outlet rate plus internal variation rate. The second production rate term is positive for the produced biomass, negative for the consumed sugar. For fermentation modeling, instantaneous material balances are employed to determine the rate of change of concentrations as a function of inlet, outlet, and reaction rate terms. The instantaneous biomass balance provides a differential equation describing the time derivative of biomass concentration. This equation accounts for the biomass outlet rate and the production rate due to bacterial growth. Similarly, the instantaneous sugar balance yields a differential equation that represents the time derivative of sugar concentration. This equation incorporates the sugar inlet rate, outlet rate, and consumption rate during the fermentation process. The previously established instantaneous biomass and sugar mass balance equations are combined with the kinetic laws governing cell growth and sugar consumption. The resulting set of differential equations is then subjected to numerical integration to provide the dynamic variations in bacteria and sugar concentrations throughout the continuous fermentation. Under a constant volumetric flow rate, Q over V, the bacteria concentration exhibits a progressive increase during the initial batch phase. Subsequent to the introduction of medium feed, this concentration experiences further augmentation before ultimately reaching a steady state. Concomitantly, the sugar concentration exhibits a decline during the initial batch. In the continuous operation, this decrease continues, ultimately stabilizing at a steady-state value. As previously inferred from the mass balance relation, the volumetric flow rate Q over V stands out as the principal operational variable in continuous fermentation. The constructed simulation model serves as a valuable tool for evaluating the impact of this volumetric flow rate on both the transient variations and steady-state values of sugar and biomass concentrations. According to the simulation findings, maximal conversion of sugar into bacterial biomass occurs at lower volumetric flow rates, indicative of an extended residence time of the medium within the stirred bioreactor. As the volumetric flow rate increases, there is a rise in steady-state residual sugar and a corresponding decrease in steady-state biomass concentration. Exceeding a certain threshold of volumetric flow rate results in a medium residence time that is too short for cell replication, leading to complete washout of cells from the fermenter. Therefore, continuous bacteria production can only be sustained at sufficiently low feeding flow rates. In summary, in this introduction to the modeling and simulation of bioprocesses, you learned the central role of simulation models to accelerate the scale-up and optimization of bioprocesses. The knowledge type of simulation models used in bioprocess engineering based on the understanding of the influencing phenomena of reaction, mass, and heat transfer and fluid flow. The construction methodology employed in developing bioreactor simulation models, which integrates instantaneous mass balances with the kinetic laws governing biotransformation processes. If interested, you can gain a deeper insight in bioprocess design and scale-up by enrolling to one of our 2 online courses, Introduction to Bioprocess Design, Scale-Up and Simulation, and Design and Cost Evaluation of Bioprocesses. For further information, please visit our Bioprocess Engineering online website or contact us at bioprocessdigital.com. We hope you found value in this introductory tutorial on bioprocesses. Your feedback is important to us, so please share your comments with us. Explore our website for more information about our comprehensive online courses in bioprocess engineering, and be sure to subscribe to our Bioprocess Engineering online channel for upcoming tutorials. Thank you for watching.